Hello, we're going to talk about straight lines in two-dimension using vectors. So let's say if I have let's draw an x and y axis right here. This is our x-axis. This is our y-axis. And let's say I have some line in space going through space right here. So this is the line right here. And let's say I have point let's say I have point A right here, and then some point B right here. Good. And then I have, let's go ahead and draw, and then there's the origin right here. Let's say that's O. And then let's say, then I have the vector OA that connects right here. So that connects here, and then I'm going to have vector OB right here. But I'm going to name, let's name this OB vector R, right? That's going to be vector R. And let's suppose that we have another vector in space that's parallel to line L. So it's going to look something like that. Trying my best to draw that out right there. That's just some vector in space, and we're going to call this just vector u, right? That's vector u that's parallel to this line. Now we can formulate a vector r, right? Look at r. R would be the vector r, which is the vector OB, but we're going to call it just vector r, right? I should put a little symbol up there to tell that a vector. What would the vector r be equal to, right? Well, that would be the sum, right? The sum of with this vector and this vector, right? So, and we're going to call this, since this is a position vector, it just goes from the origin right to A, right? We're going to call that vector, we'll just call that vector, I guess I can just write it right here. This would be vector A, right? This vector right here, OA, is just A. So this would be vector A, right? Plus, it would be AB, right? And then we're going to think about what AB is in terms of this parallel vector in here. Now, I want to make this vector right here fit into these 2 points right here, right? To fit into here. So I'd have to scale it. In this situation, it looks like it's scaled down, but maybe, you know, it could have been like a smaller vector like that. Who knows? And I might have to scale it up to fit between points A and B. But either case, if I have some scalar, let's say I have some scalar lambda, right? Lambda in the element of the real numbers, right? Good. And then I can change this vector, vector r, into the position vector A plus some lambda times whatever our vector u is, right? And I can scale it to fit into here. And what does this give us? This is what we call a this is a vector equation of a line. Good. This is what represents our vector equation. And what does it give us, right? Now remember, A is the point. A would be the point x1, y1, right? So that is some point on the graph, and then we can get every other point on this line by scaling at some vector in this u vector and find any other point, whichever way we want to go. It gives every equation on the line. So if we let u, let's say we have vector u, and that's going to be, we'll call that u sub 1, u sub 2 for its direction, right? Now I can write this equation. Now r would be every point that's in this line, right? So if we let r be, let's do a different color. Let's say right here. Let's say if r is the point, let's say x, y, right? Is that a vector equation? It is a position vector, so it'd be every point in this line. That's going to be, since this is x1, y1, this vector is x1, y1, right? Plus some scalar lambda that's going to be some real number, and then our direction is u sub 1, u sub 2, right? Good. So this is our vector equation of a line. Now, from the vector equation of a line, we can formulate something that's called the parametric equations. And simply by a parametric equation is you just take what our x coordinates are going to be equal to, and from our vector equational line, right? So our x coordinate in this situation, x would be equal to, well, x1 plus this scalar can be times that, so it'd be lambda times u sub 1, and then I wrote that as, looks like an I, so lambda times u sub 1, that looks messy, I don't like the way that looks. Good, so lambda times u sub 1, and our y coordinate is equal to y1 plus lambda u sub 2, right? And this is what we call our parametric equation. Parametric equations basically tell you what your x coordinates are going to be, and so on. So where your lambda is often called your parameter, right? But your y values are split up. So this is your parametric equation. And then I can continue from that, right? If I were to solve for lambda, for the first one, right, what would I get? Lambda, I could subtract x of 1 and divide by u sub 1. So another form for parametric equations is going to be, well, that should be, my bad, should be x minus x of 1 all over u sub 1. And this same parameter lambda would be equal, if I solve this, I'd subtract it, so it'd be y minus y sub 1 is equal to u sub 2 this time. So this is another form of parametric equations. And then finally, what we call Cartesian equations. Cartesian equations are basically our equations that we've always dealt with lines, right? So slope-intercept form, point-slope form. We're going to use point-slope form, so that would be y minus y1, right? And then it would be our slope. But what our slope be? Our slope would be, you know, our change in our y over our change in our x. So it'd be y2 over y1, right? So it'd be, I mean u2 over u1. That would be our slope. Then it's x minus x of 1, and we can change it to Cartesian form this way. Sound good? So when we went over, we got our vector equational line. It could be written like this. Then we have parametric equations. We have two forms. We can set them up separately, or we can set them like this. Here, this gives us a point on the line. This is our x and our y, our variables, and this would be our change. This would be our change in a y and a change in an x, and so on. And then we can change to Cartesian equations, right? And so on. All right, so let's go ahead and solve a couple of examples. So the first one here, it says, given that this is example 24, given that A is the point 1, 3 and B is the point 2, 5, represent AB by a vector equation, then a parametric equation, and then a Cartesian equation. So the first thing I'm going to do for A is I'm going to find the vector AB, right? What is AB going to be equal to? That would be 2 minus 1 is 1, and then 5 minus 3 is 2. So that would be the vector that's in that line, right? Good. And then I can write a vector equation R, and I can use a position vector. Now remember, R is equal to, for a vector equation, would be A, which is the position vector, plus some scalar lambda times the u that's in that line. I can just go ahead and find the vector between those 2 points, and that will be my u. So but my position vector can be any point that I know to be on the line, right? And I can use either one, but I'll pick the first one, so that's 1, 3, right? Plus some lambda, and the vector that's in this line we found to be 1, 2. Good. So 1, 2. Good. So that's our vector equation, right? For B, it wants to find the parametric equations. Well, that would simply be by taking x, and then whatever my x coordinates would be. In this situation, it would be 1 plus lambda, because 1 times lambda is this way, and then y is equal to 3 plus 2 lambda. Good. And then C, a Cartesian, right? Cartesian equation would be y minus, I'll pick this one, this would be 3 is equal to, what would be my slope? I use these 2 over 1, so that's going to be 2. And since I use this point, my x is going to be x minus 1. And then I can simplify this, and I get y minus 3 is equal to 2x minus 2. Then I add 3 to both sides, and I get y is equal to 2x plus 1 gives me my Cartesian equation of a line. And there you go. So, so we did our vector equation, we did our parametrics, and we did our Cartesian equation. Now, the next example here tells us write down a vector equation, a parametric, and a Cartesian equation for the lines through A, which is point A, which is negative 1, 2, and parallel to both of these. Now, if you notice, this vector is just in our linear combination form, and that's 2i, so it's just, this is just going a horizontal vector, right? But we'll write the parametric equation, right? It has to go through this point, so that's negative 1, 2. Then it's going to be lambda, and the vector equation, this would be 2 in the x direction, but 0 in the y, so this would be 2, 0. So that's my vector equation. My parametric would be x is equal to negative 1 plus 2 lambda, and my y would be 2 plus 0, right? This would be parametric equations. And then my Cartesian equation, well, if you look at y is just equal to 2, right? Doesn't matter where x is, y is going to be 2. This is my Cartesian equation. So my Cartesian equation is just y equals 2. Now the parametric, I need 2 equations for this in 2 dimensions, but my Cartesian equation is y is equal to 2. And then same thing can happen over here. I'm going to find my vector equation. It's got to go through that same point, so negative 1, 2. And then it's going to be lambda times, this time it's just going 3 vertically, so it's going to go 0 in the x, but then 3 in the y. And then that's my vector. And then parametric would be x is equal to just negative 1, where y is equal to 2 plus 3 lambda, right? So this is my parametric like I did before, but my Cartesian equation is just x is equal to negative 1. And you can see that this one here would be just a, if I were to graph it, it's just going to be a line that goes through 2, right? So it's going to be right here. Good. All our x coordinates, it wouldn't matter. It's going to be somewhere on this line, but the y is always the same. And for this one right here, this is just x equals negative 1, right? Right here, and that's that line that goes through x equals negative 1. The y coordinates would be depend on here, but x is always equal to negative 1. And there you go. Thanks, guys.